Artificial intelligence, it's a term that sparks both excitement and apprehension, but what exactly is it? In essence, AI is the ability of machines to perform tasks that typically require human intelligence. These tasks include learning, problem-solving, and decision-making. Imagine a computer that can understand your questions, learn from its mistakes, and even write poetry. That's the promise of AI. At the heart of AI lies machine learning, a revolutionary approach that enables computers to learn from data without explicit programming. Instead of being explicitly told what to do, machines can now learn from experience, just like humans do. This paradigm shift has unlocked unprecedented capabilities, allowing machines to tackle complex tasks that were once considered the exclusive domain of human intelligence. The implications of this technological leap are profound, touching upon nearly every aspect of our lives. From healthcare and transportation to entertainment and education, AI is poised to reshape our world in ways we are only beginning to imagine. As we delve deeper into the realm of AI, we'll uncover the mechanisms behind its remarkable capabilities and explore the transformative impact it's having on our society. Imagine teaching a child to ride a bicycle. You wouldn't simply hand them a physics textbook and expect them to understand the mechanics of balance and motion. Instead, you'd let them experiment, fall, and learn from their mistakes. This experiential learning process is crucial for their development. Just as a child learns through trial and error, machines learn through data. You wouldn't expect a child to grasp complex concepts without hands-on experience, and similarly, you can't expect a machine to perform tasks without being exposed to vast amounts of data. The process of falling and getting back up is akin to how machines iterate through data, refining their algorithms with each cycle. Each fall is a data point, each attempt a new piece of information that helps the child or the machine improve. This experiential learning process is analogous to how machines learn through data. Data is the lifeblood of AI, the raw material that fuels its cognitive abilities. Without data, AI systems would be like a child without a bicycle, unable to learn, unable to grow. Data is the lifeblood of AI, the raw material that fuels its cognitive abilities. Just as humans learn from their experiences, machines learn from the data they are fed. This data can take many forms, from images and text to sensor readings and financial transactions. The more data a machine is exposed to, the better it becomes at recognizing patterns, making predictions, and performing complex tasks. Consider a machine learning algorithm designed to identify different species of birds in images. By training on a massive dataset of bird images labeled with their respective species, the algorithm learns to distinguish subtle features that differentiate one species from another. The shape of the beak, the color of the feathers, the pattern of the wings, all these details contribute to the algorithm's ability to accurately classify birds. This data-driven approach to learning is what sets AI apart from traditional computer programs. Instead of relying on explicit instructions, AI systems can adapt and evolve their behavior based on the data they encounter. This ability to learn from experience is the key to unlocking the true potential of AI. Imagine the possibilities when AI systems are fed with diverse and extensive datasets. They can learn to perform tasks that were once thought to be the exclusive domain of human intelligence. From diagnosing diseases to driving cars, the applications are endless. The more comprehensive the data, the more nuanced the learning. For instance, an AI trained on a diverse data set of medical images can assist doctors in diagnosing conditions with remarkable accuracy. Similarly, an AI exposed to vast amounts of traffic data can make real-time decisions to navigate complex driving scenarios. Supervised learning is akin to having a teacher guide a student's learning process. Just as a teacher provides structured lessons and feedback, supervised learning algorithms rely on labeled data to learn and make predictions. Imagine a classroom setting where a teacher presents students with labeled examples, explaining the underlying concepts and relationships. The teacher might show a math problem and then demonstrate the steps to solve it, ensuring that students understand each part of the process. The students then apply this knowledge to solve new problems, receiving feedback from the teacher along the way. This iterative process helps students refine their understanding and improve their skills over time. In supervised learning, the algorithm is provided with a labeled dataset where each data point is paired with the correct output. This dataset acts as the teacher, guiding the algorithm to learn the mapping between inputs and outputs. For instance, in image recognition, the dataset would consist of images labeled with the objects they contain. Each image might be tagged with labels like cat, dog, or car, providing clear examples for the algorithm to learn from. The algorithm learns to map the input features, like pixel values in an image, to the corresponding output labels, such as cat, dog, or car. Over time, with enough labeled examples, the algorithm becomes proficient at identifying these objects in new, unseen images. This type of learning is particularly effective for tasks such as classification and regression. Classification involves assigning data points to predefined categories, while regression focuses on predicting continuous values. Classification tasks can range from identifying spam emails to diagnosing diseases based on medical images. For example, an email might be classified as spam or not spam, and a medical image might be labeled as benign or malignant. Regression, on the other hand, focuses on predicting continuous values, such as forecasting stock prices or estimating the remaining useful life of a machine. These predictions are crucial for making informed decisions in various industries. Supervised learning has found widespread applications in various domains, including natural language processing, speech recognition, and fraud detection. In natural language processing, algorithms can learn to understand and generate human language, while in speech recognition they can transcribe spoken words into text. By leveraging labeled data, supervised learning algorithms can achieve remarkable accuracy and efficiency in solving complex problems. This ability to learn from examples and improve over time makes supervised learning a powerful tool in the field of artificial intelligence. Unlike supervised learning, which relies on labeled data, unsupervised learning throws the algorithm into the deep end without a life preserver. In supervised learning, the algorithm is trained on a dataset that includes both the input data and the corresponding output labels. This means the algorithm learns from examples and can make predictions based on the patterns it has seen before. However, in unsupervised learning, there are no labels to guide the algorithm. It must navigate the data on its own, identifying patterns and structures without any prior knowledge of what it is looking for. Imagine a detective piecing together clues from a crime scene without any witnesses or suspects. The detective must rely solely on the evidence at hand, using their skills and intuition to uncover the truth. They must analyze the scene, look for patterns, and connect the dots to solve the mystery. This is similar to how unsupervised learning works, where the algorithm must find hidden patterns in the data without any external guidance. They must rely on their intuition and the ability to spot patterns to solve the case. The detective's ability to think critically and make connections between seemingly unrelated pieces of evidence is crucial. Similarly, unsupervised learning algorithms must sift through vast amounts of data, identifying patterns and relationships that are not immediately obvious. This process requires a deep understanding of the data and the ability to recognize subtle patterns that may not be apparent at first glance. In unsupervised learning, the algorithm is presented with an unlabeled dataset and tasked with finding hidden patterns and structures within the data. This can involve clustering similar data points together, identifying outliers, or reducing the dimensionality of the data to make it more manageable. The goal is to uncover the underlying structure of the data, which can provide valuable insights and informed decision-making. It's like giving a child a box of Lego bricks without an instruction manual and asking them to build something interesting. The child must use their creativity and problem-solving skills to experiment with different combinations and arrangements of the bricks. They may start by building simple structures and gradually progress to more complex designs as they gain a better understanding of how the pieces fit together. The child must explore different combinations and arrangements to create something meaningful. This process of exploration and experimentation is at the heart of unsupervised learning. The algorithm must try different approaches, test various hypotheses, and learn from the results. Over time, it can develop a deeper understanding of the data and uncover hidden patterns that were not immediately apparent. Clustering is a common unsupervised learning technique that groups similar data points together based on their shared characteristics. This can be useful in a variety of applications, such as customer segmentation, image recognition, and anomaly detection. By grouping similar data points together, the algorithm can identify patterns and relationships that may not be obvious when looking at the data as a whole. For example, a retailer might use clustering to segment its customers into different groups based on their purchasing behavior, allowing for targeted marketing campaigns. By understanding the different needs and preferences of each customer segment, the retailer can tailor its marketing efforts to better meet the needs of its customers and improve overall sales and customer satisfaction. Another important application of unsupervised learning is dimensionality reduction, which aims to simplify complex data by reducing the number of variables while preserving its essential information. This can make the data easier to analyze and visualize, and can also improve the performance of machine learning algorithms by reducing the amount of noise and redundancy in the data. This is particularly useful for dealing with high-dimensional data, such as images and text, where the sheer number of features can make analysis and computation challenging. By reducing the dimensionality of the data, the algorithm can focus on the most important features and ignore the less relevant ones, making the analysis more efficient and effective. Unsupervised learning offers a powerful set of tools for exploring and understanding data, uncovering hidden relationships, and generating insights that would be difficult or impossible to discover through manual inspection. These insights can be used to inform decision-making, improve processes, and drive innovation in a wide range of fields. Its ability to extract meaning from unstructured data makes it an invaluable asset in fields such as data mining, anomaly detection, and recommender systems. By leveraging the power of unsupervised learning, organizations can gain a deeper understanding of their data, uncover hidden opportunities, and make more informed decisions.